Swayam Prabha. Digital India. Educated India.
Hello everyone. So, last class I have already discussed about welded joint which is subjected to bending moment. Then what should be the design dimension of that welded joint. Today I will solve some problem on these topics. So, the second problem statement is like a circular beam. This is problem number 2 you can say. So, a circular beam, this is a circular beam whose length is 200 millimeter, which you can see in this figure, and its diameter is 50 millimeter, is welded to a support by means of fillet weld. So, this is generally welded here. So, this is the support. With this support generally it is welded by fillet weld. So, you know that this fillet weld is a triangle types of weld which have a leg length and throat thickness dimension. So, we have to find out the size of the weld. Here the given permissible shear stress as 100 MPa. So, first of all here what are the things given? So, here given data as permissible shear stress equal to 100 MPa and the load P is given as 10 kilonewton, but this is a circular shaft. Okay. But in previous case we have observed that was rectangular cross section, so this is a circular shaft. So, here also we will follow similar types of steps. So, first step is to find out the primary shear stress. So, here primary shear stress, this is tau 1 which is equal to, you know, this applied force P divided by cross sectional area in throat region of full weld, or you can say wall weld. So, here the cross sectional area in throat thickness position will be equal to how much? So, here it will be generally 2 into pi into r of this shaft into you can say T, or you can say 2r equal to diameter of this circular shaft d into T into pi, that also you can write. So, this is the total cross sectional area at throat location. Let us consider the throat thickness is T. So, let us consider, so here what are the things we have to find out? We have to find out throat thickness T and leg length is. So, these are the things we have to find out. So, here we consider throat thickness is T, which I am showing in this figure, you can see. So, what should be the primary shear stress here? So, primary shear stress here it will be P is given as 10 kilonewton. So, 10 into 1000 will be Newton divided by pi into diameter of this shaft, because we have to consider the cross sectional area of weld. This you should keep it in mind. So, whatever the total weld is there, that total weld cross sectional area we have to consider. That is why pi d is the periphery of this weld. Once we multiply it with this throat thickness T, so we will get total throat thickness cross sectional area. So, here it will be 10,000 divided by pi into d is 50 into T. So, its magnitude is and directly I am just putting. So, the value of these things is equal to 63.66 divided by T. It is a shear stress, so its unit is Newton per millimeter square. Now, second steps here. So, second step is to find out the bending stress. So, bending stress we know sigma b equal to m, or you can say mb into y divided by Ixx. This you should keep it in mind. So, here y should be the farthest distance of that weld from xx axis. So, here you can say this farthest distance, because what happens here you can say maximum bending stress. This we can say maximum bending stress, that I am writing. So, here what should be the maximum bending stress? This maximum bending stress will be at the periphery and perpendicular distance. What is the maximum perpendicular distance of this weld from this x axis? So, this maximum perpendicular distance of this x axis will be, here I am showing, will be this distance. So, here let us consider this element as L element. So, this in this L element generally we can get maximum bending stress. So, what is the position of this of this element from this x axis? So, the position of this element of this x axis here is y1, let this is y. So, this y will be equal to what? This y will be here your diameter divided by 2, that means radius of this shaft you can say. Okay, because here we are considering that weld is a line. That is why here we can consider, we can neglect this T by 2 term, because here if we consider this what it is called position of this weld along the center of this throat thickness, then what happens, it should be generally d by 2 plus T by 2, but here we are neglecting that T by 2 term. That is why here directly we are considering this y equal to our d by 2. So, here mb is known. So, here what is mb? Here I am just showing mb is equal to p into eccentric distance of this weld E. So, here E equal to we can say 200 millimeter. So, this will be equal to 10,000 into E is 200, and here y equal to we can say d by 2, diameter by 2, diameter by 2. So, this will be equal to our 50 by 2, that means 25 mm, and here we have to find out what is Ixx. So, mb and y is known to us. Now, we will find Ixx. This Ixx calculation now I am going to show. Here itself I am going to show this Ixx calculation. So, how to calculate this Ixx? So, now here I am just showing this Ixx calculation. So, this is the just I am drawing this thing, then it will be more clear to you. So, how to calculate this Ixx? This is the main step of this types of problem. So, this is our x axis. Now, consider an elemental section. This is the center of this shaft you can say, or you can say this is the CG of this weld, that means circular weld. So, here how to find out the Ixx, that I am going to show. So, consider an elemental section of area delta A. So, I am considering a elemental section. So, let this is the elemental section which I am representing. So, let the area of this elemental section is delta A. It is located at an angle theta with x axis. So, it is located at an angle theta with x axis and subtends an angle d theta, because this small elemental area, let us makes an angle d theta like this, which I am showing in this figure. Now, here the radius of this shaft, or you can say weld, circular weld, or you can say annular types of weld, is given as r. So, here r is what? R is generally considered as d by 2. So, here what is the distance of this small elemental area delta A from this x axis? Let this distance is y1. Okay. So, y1 we can easily find out. So, what will be the y1? Because this radius r is given, this r is actually d by 2. So, let this is r. So, here this y1 will be, you can say, r sin theta. What I am telling, understand? This you should keep it in mind. So, here also we will use what it is called parallel axis theorem, you can say. So, we know, first of all we will find out what is the moment of inertia of this small elemental area delta A about this capital X axis. So, here we can easily find what is the small elemental area delta A. A small elemental area delta A will be, let this is the thickness of the throat thickness of this weld T, and we know this T into this, because we consider this is a what? This is a small rectangular element that we can consider. So, what is this thickness of this weld is given T, and this d theta makes a length. This length is, let's what should be the length? This length is equal to your r d theta, which is very well known to you. So, because r into d theta is given as this small elemental length. So, what should be the small elemental cross sectional area? So, delta will be your throat thickness T into this small elemental length is r d theta, that we can say. So, here we are getting as T r d theta. Now, here this small elemental areas, we will find out first the small elemental areas moment of inertia about x axis. So, small elemental areas moment of inertia about x axis we can easily find out. So, this small elemental areas moment of inertia let is considered as delta I x x. So, this will be equal to what? This small elemental area delta A into the perpendicular distance from this small elemental area from this x axis. So, what is the perpendicular distance here? This perpendicular distance is here as y1 square. This is the common theory of this moment of inertia calculation, because we are calculating these things with respect to x axis, this capital X axis. This you should keep it in mind. That is why we have to consider that area into perpendicular distance of that area from that axis about which we are finding out the moment of inertia. This you should keep it in mind. Okay. So, by this what we are getting? We are getting, we know delta A equal to T r d theta, and y1 also I have already shown, y1 equal to r sin theta, this whole square. So, this we are getting as T r d theta into r square sin square theta. So, this will be equal to T r q sin square theta d theta. Now, what should be the total annulus moment of inertia of this weld about this x axis? This we can find out by integration. So, here the moment of inertia, so this is the small elemental areas moment of inertia about x axis. This I am representing by equation number 1. So, here I am showing this thing. So, to find the total moment of inertia of this circular weld by the method of integration, you can say, by the method of integration. How it is, that I am going to show. Because here you see this is the moment of inertia of an annular fillet weld, which is obtained by integrating the equation number 1. So, here the total moment of inertia about this x axis will be integration of here 2 into integration of 0 to pi, you can say T r q sin square theta d theta. By method of integration, here I am writing of equation number 1, and the limit is here you can say 2 into integration of 0 to pi. So, here I am just taking out of this 2 t r q. So, this will be 0 to pi sin square theta d theta. Now, to do integration sin square theta d theta, here we will use some common techniques, like we know cos square theta minus sin square theta equal to cos 2 theta. This is very well known to you. So, we can say 1 minus cos square theta equal to 1 minus sin square theta minus sin square theta equal to cos 2 theta, correct. So, we can say sin square theta equal to 1 minus cos 2 theta divided by 2, correct. So, what are the condition formulation here we are using? This is one formulation, another one formulation is sin square theta cos square theta equal to 1. By using these two formulation, generally we can get sin square theta equal to 1 minus cos 2 theta divided by 2. So, these things here I am putting. So, 2 t r q integration of 0 to pi. So, sin square theta, instead of sin square theta here I am putting 1 minus cos 2 theta divided by 2 d theta. So, this 2 will be cancelled out, you can say. So, here we are getting t r q. So, if we do this integration, so integration of 0 to pi d theta minus integration of 0 to pi cos 2 theta d theta. So, here t r q d theta means theta, its limit is varying from 0 to pi, and this sin 2 theta, that is very well known to you. So, I am directly putting this thing. So, this you can write as sin 2 theta by 2, its limit also varying from 0 to pi. Okay. Now, here t r q for this theta, here we can get pi, and for this 0 to pi sin 2 theta it will be 0. So, here you can say this pi t r q is equal to the Ixx of this full weld, or we can say Ixx is of this annular fillet weld. Okay. So, I have already calculated this Ixx value. So, we can easily find out what is this sigma b. Now, Ixx is known to us. So, what will be the sigma b? So, the bending stress sigma b will be equal to mb, here you can say y maximum perpendicular distance between x axis and this weld. I have already shown you what is this y max divided by Ixx. So, mb is already I have shown in previous slide, that is 10 into 1000 into y max, here is 50 divided by 2 divided by Ixx, here I am directly putting pi t r q. So, if we just put all these things, 10 into 1000 into 25 divided by pi, r is 25 to the power q into t, here we are getting sigma b equal to, directly I am just showing this thing. So, sigma b here we are getting as 1018.59 divided by T Newton per mm square. So, now sigma b is known to us, tau 1 is known to us. So, we can easily find out what is the maximum shear stress. So, the third step of this problem is maximum shear stress, maximum shear stress calculation. So, what should be the maximum shear stress calculation? This formulation is very well known to us. We know that is sigma b by 2 whole square plus tau 1 whole square. So, this sigma b by 2 is known to us, that is 1018.59 divided by 2 t square, and tau 1 also I have already calculated, 63.66 divided by t divided by t whole square. So, this is equal to 513.26 divided by t, its unit will be the unit of stress, that is Newton per mm square. Now, the fourth step is to find the size of the weld. So, we have to find the size of the weld. So, to find out the size of the weld, here we know this permissible shear stress. So, the permissible shear stress sigma p we have to compare with this maximum shear stress. So, tau p is given as 100 MPa. So, 100 MPa means 100 Newton per millimeter square. This will be equal to 513.26 divided by t. So, from here we get t equal to 5.13 millimeter. So, the leg length will be equal to A is equal to your t by 0.707, that is 5.13 divided by 707, which will be equal to 7.26 millimeter. We can consider the next digit, that next full digit, that is 8 mm. because if we can consider a little bit higher dimension of leg length, then our structure will be more safe, correct. That is why we can consider. So, this is the leg length and this is the throat thickness. So, by this generally we can design these types of welded joint. So, beforehand if you have some structure which is like this, then if somebody asks it is subjected to some load P, then what should be the welding dimension there you should use. So, if we follow this step and if we use these types of what it is called welding dimension in that particular joint, then your structure will be safe. But if we will not calculate these things like this way, and if you directly do some welding without considering any steps, then what happens, your thing can be fail. That is why you should follow some standard design procedure before going to do actual one. Okay. Now, we will solve another problem which is little bit different type of problem you can say. So, this problem statement is like a beam of rectangular cross section which is welded to a support by means of fillet weld as shown in this figure. So, determine the size of the welds if the permissible shear stress in the weld is limited to 75 MPa. So, here is also more or less similar problem of first problem, but in first problem we consider 2 parallel weld only, but here we consider 4 weld because 2 vertical and 2 horizontal weld. So, that is why here the calculation and other steps will be little bit different. So, what should be the difference, that I will now show. So, here the given data as applied force P equal to 25 kilonewton, eccentric distance is given as 500 millimeter and permissible shear stress given as 75 MPa. Now, what we have to find out? We have to find out the dimension of this weld, means we have to find throat thickness. So, let us consider the throat thickness equal to T. So, this we have to find out. Also, we have to find out what is leg length. So, these things we have to find out. So, here also we will follow the same steps. So, here also we will follow the same step, like the first step is to find the primary shear stress. Okay. So, here what should be the primary shear stress? So, tau 1 equal to your P by total cross sectional area of all welds. So, here total cross sectional area of all weld is how much? Here you can see 2 horizontal weld of 100 millimeter length. So, let us consider the throat thickness here of this wall weld is T. If the throat thickness is T and length of vertical and horizontal weld is given as 100 and 150. So, we can easily find out here 2 horizontal weld. So, 2 horizontal weld cross section will be 2 into 100 into T, and there is 2 vertical weld also there. So, 2 into whose length of this vertical weld is 150 mm and its throat thickness is T. So, this will give us 500 T, correct. So, the primary shear stress, this is the cross sectional area of this weld, correct. So, its unit will be millimeter square. So, primary shear stress tau 1 will be equal to P, which is 25 into 1000 Newton divided by cross sectional area of all weld, which is equal to 500 T. This will be just you can see 50 divided by T. So, its unit will be Newton per millimeter square. Now, second step, why I am solving this problem, because here you will get some idea to consider farthest distance of weld to find out the maximum shear stress, that I will show. Okay. So, second step is bending stress calculation. So, bending stress calculation we know sigma b equal to bending moment m b into, you can say here y, here this should be y max divided by I x x. So, I x x should be the moment of inertia about x x axis of all weld, that also I will show you. So, here m b is given, or you can say m b we can calculate by using p into eccentric distance, which is already given. So, this is equal to, you can say p is given as 25 into this 1000 into E is your 500. So, this we can get as MB, so unit will be Newton millimeter, because this is force into distance. Now, what is Y max here? This is the main step of this weld, you can say. So, here we should consider the farthest weld perpendicular distance between two axes. So, this is the farthest weld, here you can see, because here this is the CG of this wall weld, this you can easily find out, this is a rectangular cross section. So, we can easily find out. So, CG. So, here this farthest weld from this capital XX axis, you can say, will be the any one of this horizontal weld, because here this you can say the distance between this what it is called horizontal weld is equal to how much here? This horizontal weld distance is XX axis is how much here is 75 mm, this you can say. So, here the farthest weld perpendicular distance of this axis, you can say, that means XX axis, and you can say x1 axis generally is the y max distance. We should consider this farthest weld, because we already well familiar that in case of a rectangular cross section, generally the bending stress distribution is how? The bending stress distribution, you can say maximum is the top fiber and it's gradually decrease and it's come to 0, that let this is the neutral axis. So, about neutral axis, top fiber generally is subjected to tensile types of stress, bending stress, and this is generally the maximum sigma b maximum. So, the farthest distance from this neutral axis, or you can say CG of this weld axis, have the maximum bending stress. That is why here we should consider this maximum on to design this dimension of the weld. This you should keep it in mind. That is why generally here we have to consider the weld which is farthest position from the neutral axis, or you can say from this CG axis, that is XX axis, capital XX axis. So, here Y max equal to 150 divided by 2, that is you can say 75 millimeter. So, these two things already I have calculated. Now, I will show you how to find out this IXX of this 4 weld. So, to find out IXX of this 4 weld, so let this is our XX axis. So, how to find out IXX? So, this is already given as T, and this height you can let this is I am representing in terms of A's, and this I am representing in terms of B. So, what should be the IXX of this 4 weld? So, here 2 vertical weld is there and 2 horizontal weld are there. So, IXX for vertical weld, here we can easily find out that I am representing IXXV, or we can say moment of inertia of vertical two welds will be what? 2 into, because here x axis is passing through the center of this vertical weld itself. So, we can easily find out 2 into, here this will be your T, here it will be HQ divided by 12. Now, so this is moment of inertia of vertical weld. Now, moment of inertia of horizontal two welds, here we have to use parallel axis theorem, because here you see there is a distance between horizontal weld and its x axis. So, here we have to use what it is called parallel axis theorem. So, let us consider this is the CG of this one weld. So, this is the CG which I am representing as G small g 1. So, here we have to use, here I am writing, then it will be more clear, I have to use parallel axis theorem. So, what should be this Ixx of this horizontal weld, because two symmetric weld we can say 2. So, 2 weld will find. So, 2 into moment of inertia about its own axis, you can say I, let this is your x1 axis. So, I x1 or you can say g1 axis plus area of that weld A into perpendicular distance between this x axis and this x1 axis. So, this is let's our this distance is let's y. So, you can say y square. Okay. So, this will be equal to, directly I am putting here. So, I x1 will be generally here it will be B into TQ divided by 12 plus area of this weld will be a small a will be our T into B, and y is will be here h by 2, you can say h by 2 square, correct. Now, here one thing you should keep it in mind, as T is, you can say mass smaller than B and H. So, here we can neglect TQ terms. What I am telling, understand? That is why here TQ terms we will neglect from here. So, the moment of inertia of all welds, will be equal to, let us Ixx here I am representing, equal to your Ixx V plus Ixx horizontal component H. So, here we are neglecting this TQ term, you can say this TQ term we are neglecting. So, what will be the moment of inertia here we can get? So, here we can get moment of inertia equal to 2 THQ divided by 12 plus 2 into T into B into H by 2 whole square, correct, because we neglect TQ term. So, by putting H equal to 150 mm and B equal to 100 mm, we get Ixx, directly I am just putting the thing. So, Ixx equal to 75 into 150 whole square into T millimeter to the power 4. So, we can easily find out sigma b, that means bending stress sigma b equal to, now I am just directly finding out this sigma b. So, sigma b equal to 2500 Newton into eccentric distance is 500 into y max, here we get as 75 and Ixx of all weld we got as 75 into 150 square into T. So, this will give us sigma b equal to 555.55 divided by T Newton per mm square. Now, we will use the third step. So, third step is to find out the maximum shear stress. So, maximum shear stress is very well known to you, how to find it. Tau max equal to generally your sigma b by 2 whole square plus tau 1 square. So, here sigma b by 2 already I have calculated, that is 555.55 you can say divided by T. So, this will be 2 T whole square plus tau 1 is 50 by T whole square. So, sigma max we are getting as 282.24 divided by T Newton per mm square. Now, the fourth step here, the last step, that is size of the weld, size of the weld. So, what should be the size of the weld? Here the permissible shear stress is given as 75 Newton per millimeter square. So, we know here we will use permissible shear stress equal to this maximum shear stress condition, because this is the permissible shear stress which is given as 75 and tau max we have already calculated, that is 282.24 divided by T, which is a function of T. From here we can easily find out what is the throat thickness T. So, we get throat thickness equal to 3.76 millimeter. So, the leg length will be equal to H equal to your T by 0.707. So, this will give us 5.32 millimeter, or we can consider this equal to 6 millimeter. So, this is the design throat thickness and weld leg length. Okay. This way generally we can find out the design dimension of a weld for a weld structure subjected to bending moment. So, these are the references which I have followed for this lecture, that means for this types of analysis of welded joint. Thank you.